In this video, we will start to look at the relationship between equations and graphs. The first thing to note is that an expression is different from an equation. A mathematical expression is a collection of numbers, variables, and operations without an equal sign. When we have one expression equal to another expression, we end up getting an equation. There are three possibilities for equations. The first is that they are never true, like 1 plus 1 equal to 3, or the absolute value of x minus 3 equal to negative 4. As we know, the absolute value means the distance between two values, and distance can't be negative. So there's no value for x that will make that equation true. The next case is when equations are sometimes true, like when 2x plus 5 equal to 17 is true when x is equal to 6. We can also have a two-variable equation, like y equal to x squared, which is sometimes true. There are some pairs of values for x and y, like 0, 0, negative 3, 9, or 5 and 25, which make the equation true. Those aren't the only points, but there are also points such as 5, 26, which are not true, which do not lie on that graph. The third possibility is when the equation is always true. In this case, we have negative 3 all squared minus 2 equal to 7. 9 minus 2 equals 7. This is an always true case. We also have 2x plus 3x equal to 5x, so that 5x equals 5x is true no matter what value is substituted for x. We also have something like a plus b all squared, which when we expand is equal to a squared plus 2ab plus b squared. An always true equation has a special name called an identity, because the left side and the right side are identical to each other. Let's go ahead and explore this idea in a bit more detail. For question 1, we want to know, is the equation always, sometimes, or never true? We expand the left side, which gives us x squared plus 8x plus 16 minus 5x equals x squared minus 9. Then when we simplify, we notice that we've got an x squared on both sides, so we can subtract x squared from both sides of the equation, and then simplify 8x minus 5x to get 3x plus 16 equal to negative 9. We can continue rearranging and get 3x is equal to negative 9 minus 16, or negative 25, and then we can solve for x, which is negative 25 over 3. Getting a solution here for x tells us that the original equation in part A is true whenever x is equal to negative 25 thirds. So this is a sometimes true equation. It's sometimes true for the value of x that we found to solve the equation, negative 25 over 3. Let's do the same thing in part B. We'll expand both sides and we see if we get something that can be solved for x, or something that indicates false, or something that tells us always true. When we expand the left side and the right side, we can start to simplify the equation by subtracting x squared from both sides. We can then take a look at simplifying and getting 6x plus 1 equals 6x plus 9. Subtracting 6x from both sides of the equation gives us a false statement because 1 doesn't equal 9. So this is never true. There is no value for x which solves that equation. In part C, again, we expand and simplify both sides. When we square the left-hand side, we see that it's identical to the right-hand side of the equation. We could continue simplifying by subtracting like terms and get something that says negative 4x equals negative 4x, but ultimately we get that 0 equals 0, which is a true statement. And so therefore this is an always true statement or an identity. We are going to look at graphs in the xy plane in 2 dimensions, and in particular, a graph is a relationship between the x and the y variables. Now, a special kind of a relationship or relation is a function, where each input variable is related to only one output. Let's use the definition of a function to see if each relationship between the input x and the output y is a function. In part A, we have the input is the set of puppies, and y, the output, is the set of mother dogs. Each puppy can have only one mother dog, and therefore we have a function because each input can map to or be related to only one output. In part B, we've swapped the input and the output, so x is now the set of mother dogs, but because each mother can have more than one puppy, one input does not map to only one output. One input can map to more than one output, and as a result, this is not an example of a function. In part C, we have that the input is the set of lengths of a square, and y is the set of the areas of the square. There's a unique relationship between the length of the square and the area. So each length can only have one area. For example, if a length is 3, then a square can have an area only of 9. So each input maps to only one output, and we have a function. Similarly, in part D, we've swapped the inputs and the outputs, but again, each area has a unique length. So each area input maps to only one length output. And so here, we have a function. I'm using the double arrow heading towards the right to show maps to or implies. This is a common terminology in mathematics. A really valuable tool that we have in our toolbox for solving is solving graphically. Oftentimes we would take an equation like this, x squared minus x minus 2 equal to 0, and solve it algebraically. But I'm going to color code this, and I'm going to rearrange it so that I have a blue expression on the left, which is y equals x squared, and a red expression, y equal to x plus 2, on the right. Then the solutions to the original single variable equation is the same as finding the x-coordinates of the points of intersection for the blue and the red graphs. When we find points of intersection, we have both x and y coordinates, but once we find the points of intersection in Desmos, we can extract only the x-coordinates to come up with the solution to the original equation. So we've got 2 points of intersection, -1, 1, and 2, 4. But only the x-coordinates will solve the original equation. So in part B, it says to state the coordinates of the intersection points as ordered pairs. And we have an or here because the point can't be both at the first and the second point at the same time. Now to solve the original equation that only had an x in it, we take the x-coordinate of the intersection points. It's a good idea to check our solutions. We want to make sure that replacing x with -1 makes the equation true. -1 squared minus -1, take away 2. We're wondering, does that equal to 0? We get 1 plus 1 minus 2. Still wondering, does that equal to 0? Now we get 0 equals 0, which is true. And that was true for the value of x equal to -1. So we know that that's a solution. We repeat the same check with the other potential x solution. Substituting 2 into the original equation gives us 4 minus 2 minus 2 equal to 0, which we're wondering, is that true? So we write a question mark. Now we get something that is true, 0 equals 0. Therefore, the value x equal to 2 is also a solution to the equation. We are going to be looking into graphs and functions in detail, and we want to take advantage of some special properties, things like x-intercepts, y-intercepts, symmetry, transformations, domain and range, among other things that we will see later in the course. To find an x-intercept or a y-intercept of the graph, we want to recognize that they are special points, intersection points between the graph and the x-axis for an x-intercept, and the graph and the y-axis for a y-intercept. When we look at the x-axis, we know that it's a horizontal line where all of the heights are 0. So the equation of the x-axis is y equal to 0. And therefore, an x-intercept is the value of x that makes y equal to 0. Similarly, the y-axis is a vertical line where if we go up and down, the y-coordinate changes, but the x value is always 0. So the y-intercept is the value for y that makes x equal to 0, which is the equation of the y-axis. Now we also recognize that we have two equations, some graph, maybe like this curve, and we are finding the intersection point of the system of two equations, namely the given equation, and for the x-intercept, we're also intersecting with the horizontal line y equal to 0. Again, that's the x-axis. Depending on the shape of the graph, we may end up with no, one, or more than one x-intercept for the function, and we will spend the course looking at different kinds of functions to understand the behavior and to predict how many x-intercepts we will have. The y-intercept is the intersection point of the system of two equations, described again by the given equation, and the vertical line x equal to 0. Again, the vertical line x equal to 0 is just the y-axis. Now for the quick sketch I drew, there were actually 3 different x-intercepts of that function. But for a y-intercept, there can never be more than one. And I'd like you to think about why that is based on some of the properties and the ideas of functions we've been talking about already. Another useful property we will talk about for functions is a reflection. A reflection is a flip through a line called an axis of symmetry. Now remember, if we want to ignore a negative sign of a number or variable, we use the absolute value. But if we want to change the sign of a number or a variable, we multiply by -1. So a reflection has to do with changing the sign of the number or the variable. If we change the sign of the x-coordinate of every point, then we get a horizontal reflection, which flips the left to the right or the right to the left. And if we change the sign of the y-coordinate of every point in a graph, this results in a vertical reflection, where the bottom flips to the top and the top flips to the bottom. So if we perform a horizontal reflection on the point pi, -7, we will change the sign of the x-coordinate, resulting in the new point -pi, -7. Similarly, a vertical reflection will change the sign of the y-coordinate, which gives us the new point pi, 7. And a rotation of a point is actually both a horizontal and a vertical reflection, which means we change the sign of both the x and the y coordinates. Now that we have some reflection basics, we can talk about symmetry. A line of symmetry is a mirror line through which an object is reflected. Rotating 180 degrees around the origin is the same as reflecting through both the x and the y axes. And we have a couple of different types of symmetry of graphs. The x-axis symmetry means that the x-axis is the line of symmetry. Y-axis symmetry means that the y-axis is the line of symmetry, and it has the name of even symmetry. X-axis symmetry doesn't have another name. In fact, odd symmetry means rotating 180 degrees around the origin. In this next example, we are going to reflect point P so that the new point has various symmetries with P. In part A, we are going to reflect through the x-axis, and when we do that, point P changes its y-coordinate from a positive to a -2. And so the coordinates of A are located at -3, -2, and since we've reflected the top and flipped it to the bottom, we have performed a vertical reflection. Now we've done this through the x-axis, whose equation is y = 0. In part B, we are going to reflect P through the y-axis, which is actually going from the left to the right, and this is a change in sign of the x-coordinate. So the coordinates of B are 3, -2. This results in a horizontal reflection of point P to point B. And lastly, in part C, we want to have origin symmetry with P, so we rotate 180 degrees about the origin, which is the same as either reflecting vertically and then horizontally, or horizontally first and then vertically. We get a point in quadrant number 4, where we have changed the signs for both x and y. Transformations are other kinds of transformations we perform on graphs. They are really shifts, right or left, or up or down, caused by adding a positive or a negative constant to the x and the y coordinates. If we want to translate the point -3, 5, right 3 spaces and down 7 spaces, we're really forming a right triangle with direction. We have a start point and a finish point, indicated by the direction of motion from the translations. We can make a hypotenuse with a direction, and that would form the vector from the initial point of -3, 5 to the final point of 0, -2. Numerically, we take our starting x and y coordinates and we add a +3 to the x coordinate and we add a -7 to the y coordinate. Doing that gives us the new coordinates for the final point, namely 0, -2. In math, we study sets. The domain is the set of all the input values, and the range is the set of all the output values in a graph or relation or function. So here we have a relation given by a set of points, and the domain is going to be contained in the set, that's what that curly bracket means, of -1, which we don't need to write twice, and 3 and 8. The range will be the set of all the y-coordinates, and if we take a look, we see that the y-coordinates are not all in order, so we do like to list them in order, starting with -4, and then 2, 5, and 9. So we've listed the domain and the range, but we often want to find out if the relation is actually a function. And we do this with a mapping diagram. I'm going to put all the inputs in the first oval, and then I'm going to put all of the outputs in the second one. And I'm going to connect them from one input to its corresponding output pair using an arrow. So I know that 8 maps to 9, and I know that 3 maps to -4, and then I also know that -1 maps to 2 different outputs, namely to 2 and to 5. And so that input arrow branches or splits off into 2 outputs. And so that's a good visual way to see that we do not have a function, because the input of -1 maps to or corresponds to 2 different output values, namely the output values of 2 and 5. To understand domain a little bit more deeply, we need to talk about undefined numbers. Numerical expressions are well defined if they produce a single, real, and finite answer. 6 divided by 2 is a well-defined numerical expression because it produces the single, real, and finite answer of 3. Other numerical expressions are not well defined, such as 0 divided by 0, 3 divided by 0, or the square root of -9. We will deepen our understanding as we go through the course, but for now, we just want to avoid dividing by 0 or taking an even root, like a square root or a fourth root, of any negative quantity. So let's look at number 13 to see if there are any restrictions on x according to this function. First of all, we know that we can't divide by 0, so that denominators cannot be 0. And here we have a variable expression in the denominator. So if we were to say x plus 6 can't be equal to 0 and solve, that tells us that x can't be -6. Furthermore, we also know that we have an even root, a square root, and the radicand, which is the expression inside the root, cannot be a negative number. And therefore the radicand of the even root has to be greater than or equal to 0. So setting up a condition on the radicand gives us 8 minus 2x greater than or equal to 0. And we can solve that inequality, 8 greater than or equal to 2x, and ultimately 4 is greater than or equal to x. This gives us 2 conditions that must be true about x. The first condition is that x cannot equal -6, and the second condition is that x must be less than or equal to 4. So if we plot 4 on the number line and we go to the left, we see that there are really 2 branches of the green solution. One that is less than -6 and the other that is between -6 and 4, excluding 6, but including 4. The last property of functions and graphs that we will look at now is really not a property of a function, but it is a function, a linear function. When we have a line, we can form hypotenuses of a family of similar triangles. And those similar triangles have height to base ratios that are in proportion, that are equivalent fractions. And so this is the fundamental concept or the essence of being a line, being linear, line-like. We have constant slope, we have a constant direction, we have a constant angle of inclination or of depression from a horizontal line. And so we can see here that we've got a red and a green pair of triangles that are not the same, but they are similar. They have all the same angles. As a result, the sides of the triangles are in proportion, and therefore we can make fractions out of the sides, which is constant from one fraction to the next. And we can do that with our slope fraction to get the rise over the run is equivalent to be a over b. So just to summarize a few bits of information about slope, we have our slope fraction delta y over delta x, utilizing the change final minus initial y and final minus initial x. We have that lines that are parallel have equal slopes. Meanwhile, if slopes are negative reciprocals, then 2 lines are perpendicular. If the run delta x is equal to 0, then we have vertical lines, and we can write the equation of a vertical line as x equal to a constant. Meanwhile, if the rise delta y equals 0, then we have horizontal lines which have equations of y equal to a constant. And lastly, we know that the slope of any horizontal line is 0 because we have 0 rise over non-zero run, but the slope of any vertical line is undefined because we have a non-zero rise over a 0 run. The last thing that we'll take a look at are the various forms that we can write the equation of a line. If we have the slope and any point on the line, which we can call h comma k, we can use the point-slope form of a line. We sometimes write that as y minus y1 equals m times x minus x1. However, I don't like using subscripts, so I would like to replace h and k instead of x1 and y1. The next form of the line is the slope-intercept form. We still have the slope m, but this time we have a special point, namely the y-intercept. In this case, h is equal to 0 and k is equal to b. In this way, the slope-intercept form is a special case of the more general point-slope form. Another form that's not as familiar is the intercept form. If we have x over a plus y over b equal to 1, then a comma 0 is the x-intercept and 0 comma b is the y-intercept. It's really key to notice that the intercept form is equal to 1 on the right-hand side. The last form of the equation of a line is the standard form, but the a, b, and c in this form do not actually mean anything about the graph of the line. When we write the standard form, we like to put it in simplest form. So we make sure that the capital A is a positive number and that the capital A, B, and C values are not fractions and that they don't have any common factors. So, for example, if we were to write 2x plus 4y is equal to 6, we can see that the 2, 4, and the 6 have a common factor of 2. So we would divide the entire equation by 2 to put the equation in simplest form and get rid of any common factors. Now we've got some basic information about lines and other properties about functions and graphs. Let's put them together and apply them to solve some problems.